So welcome everyone. I'll be monitoring the chat on a second screen. So there's a specific chat for the session. And so if anybody has any question, feel free to ask. So I guess it's time, so I'll get started. The subject of today is prediction with missing values, so machine learning with missing values. And it's a part of a broader topic that I'm interested in on what I call dirty data science. So why is this topic important? Well, it's quite famous that a significant fraction of the time in data science is to prepare the data. There's this big joke that we spend 80% of the time preparing the data and 20% of the time complaining about the need to prepare the data. So I guess today I want to cover a specific aspect of data quality, which is that of missing values. And this talk will kind of have kind of two aspects to it. One is discussing the concepts, the big picture ideas, which are quite general and are not related to specific software implementation. And then I'll be talking about how all these ideas can be instantiated with scikit-learn. So the problem we're interested in is the following. We're given a data table that comes with missing values, so it's not fully observed, and we're interested in building a predictive model from this table. Now, I say building a predictive model, but it's really a statistical estimation problem that is one of relating the output, so the prediction target, which here is the wage, to a bunch of different attributes. Some of them are sometimes not observed. Now, this situation arises often in many applications, in particular things where data is related to human beings, whether it's automatically input or manually input. And so the question is why we might have those missing values which I have represented here with NA, which means not available. And so why might I have those missing values? Well, it could be that the value has not been inputted. So for instance, if we're on a survey and the people who are surveyed chose not to reply, it could be because the data has been merged across several sources, and in some sources the value is available, some sources the value is not available. It could also be because the data is related to a sensor and the sensor was failing. And I guess this sensor failure data is one that is more related to signals rather than social science applications. Okay, so the problem is we need to build a predictive model that starts from the table we have here, and this table has missing values and goes to a given output. And the goal is really to build the best predictive model. So given this table, what can I say? What is the best guess that I can have about the wage of the current people? Now, there may be many other data preparation steps related to build this model, but today we're focusing on the missing value. So I want to cover a bunch of different things. I want to start with the classic missing value framework in statistics, and then I'll move forward, and I'll basically move forward on more and more advanced ways of tackling this. But I'll make sure that aside from the last section on neural networks, I'll make sure that everything can actually be implemented quite easily. And so there is a fair amount of information And it would really help me if when anybody has any question, you just ask those questions in the chat. And if you just want to say hi in the chat, it makes me happy because I have the feeling that I have an audience. Okay, so let me start with the classic missing value framework. And this is a very old theory that has been developed for many years and that underlies most of the advice that you'll have on prediction with missing values. Well, actually not on prediction with missing values, on statistics with missing values, and we'll see that there is a small difference. So it's a classic statistical point of view, and the underlying model is that we are given a data distribution. Well, we're looking for a data distribution for the complete data, so there's a data generative process with a model for the complete data X. And then there is another random process that creates data loss, occlusion. And so classically, we model those two data generating processes. And classically, we're interested in the, well, we assume we're interested in the distribution for the complete data. And we assume we're not interested in the random process that occludes the entry, because if I do a survey, I might not be interested in why people did not report their age, for instance. I might be interested in the link between the age and the wage, but not in why they haven't reported the age. And so there is a setting which is known missing at random, and hang on tight for a minute with me. So in this setting, we assume that for the values that we have not observed, the probabilities that they're missing does not observe on this missing value. So if I have not observed the age, the probability that I'm not observing the age is independent of the age. Okay? In other terms, two records, two observations where the age is not observed have the exact same probability of being observed, whatever the age. Okay? And this situation, the missing at random situation, is a very important one because there's a very important theorem from Rubin in 76 that tells us that in this situation, I can do maximum likelihood inference for observed data while ignoring the unobserved value. And if I do this, I will get a maximum likelihood estimate of model A, which is of the completely observed data. So under MAR settings, I can do inferences on the data that I have observed and still get a statistical model that represents the fully observed data, which I do not have. So this is a very important theorem because it tells me that I can use this data with missing values and still have conclusions on the data without missing values. And this is somewhat, the central piece of statistics with missing values. And so to give you, well, to go a bit further, we can say, so I've described a missing at random situation. There is the missing completely at random situation, which is the easiest to understand, is that basically missingness is independent from the values. So it's just basically randomly dropping data. And then there is all the rest, which is missing not at random. And missing not at random doesn't have this property. And we can't ignore the fact that we have missing values. We need to model those missing values. And I'll give you a bit of intuition on how we do that. So here, just to set the picture, I've shown the completely observed data on the left. And I've shown a missing completely at random situation where you can see that I've just, dropped a bunch of data points. And then I've shown a missing not at random situation. And what you can see in the missing not at random situation is that I have some data points that are partially observed, and those are more likely to be partially observed for high values of x1 and x2. So what you can see here is that in a missing not at random situation, we're dropping data, well, we're partially observing data in a way that's not independent from the underlying values. And so our observed distribution has biases compared to the underlying full data distribution. So, really this intuition is an important one. Sometimes, often actually, my partially observed values do not have the same distribution as my underlying full set of observations. And so the problem here is that if I do statistical inference on the data that I have, I may have a result that does not reflect the underlying distribution. That's the core problem of the classic statistics point of view. Now, I want to say that we're not really going to share the goals with the classic statistic point of view. So we're going to depart a bit from this view for two reasons. One is that there isn't always a non-observed value. So I may be asking the age of the spouse, but if the individual is single, the answer has no answer. And so it's not like there is a fully observed data distribution that I can reason upon. And second, our goal here is not to do maximum likelihood inference. We're not doing statistic and parametric models. We are doing machine learning, and our goal is to do prediction, and prediction can be a statistical purpose, but it's not related to modeling the fully observed data. And so that leads us to different trade-offs, and I'll cover this. Now, if we go back to the standard practice of statistics with missing values, maybe the tool that is most easy to use is that of imputation. So the idea is that we will fill in the missing information. So by replacing unobserved value by likely values, typically using other information. For instance, I could say that a very experienced employee is more likely to have been hired a while ago, okay? And there is a large statistical literature on this. And it's important, by the way, to have in mind that it's in general granted on the missing at random situation. So the idea that the data where I've lost observation is representative of the full data set. But it doesn't fully answers the need of machine learning because it doesn't discuss how to complete the test set using only the train set, which is important if I want to put a prediction model, apply a prediction model on the test set. I need to complete the missing values. It also doesn't tell us how we should be using the prediction target Y. Okay, so just to recap a bit on the classical view on missing values, this classical view is really related to estimating the parameters of a parametric model of the fully observed data. And in this classical view, the missing values are seen as a form of nuisance that we would like to forget, that we would like not to be there. Our view here is different. Our view is that the data has missing values and we just need to cope with it. And we just want to predict the best guess of our prediction target with those missing values. And I'll show you that it will lead to different trade-offs. So now I'll talk a bit about how we may try to fix machine learning procedures. So take existing machine learning procedures and get them to run on a table like this. First problem is, why don't those machine learning procedures work out of the box? You know, they should. And actually, you know, one of the reasons is that machine learning models work better with numerical values. And the reason is that those numerical values sit in a vector space, a space that is well structured. So, you know, I can say that an age of 33 is close to an age of 44 and of 34, and is further away than an age of 44. And so the machine learning uses this structure to extrapolate. Now I can't say this for missing values. And so that literally breaks the underlying interpolation that drives machine learning. So it's more than an implementation problem. It's really the fact that where we expect numerical values, bang, we have a symbol, which is NA. Now, there is a set of features for which the problem is different, and those are the categorical entries, because the categorical entries are not continuous. They don't have this nice continuous space. They're already discrete. And I'd like to say that the missing value problem for categorical entries can be modeled in a fairly easy one. And we'll see why later. But really, the simple situation here is just to create a special category missing and just treat it as one category out of many. And this way we can model missingness. And once again, this might be a different trade-off if you're trying to estimate a model of your fully observed data. But here what we're really trying to do is to do the best prediction given the partially observed data. So the rest of the talk will really focus on having missing value in numerical variables. And the reason is that really most of the problems can be solved when they're categorical by creating a specific category which is missing. So the first thing I want to stress is that it's not just simply a question of representing missingness as an extra categorical mask. So that's one thing that works, is to say, well, I'm just going to add a feature that's a discrete feature, it's a binary feature that tells me whether a value is observed or not. And you know, once I've done this, I can represent my data. And then I can feed this in a standard machine learning model. And here my argument is that it's a theoretical argument, but even with a very simple data generating model, a linear data generating model, if theoretically we compute the best predictor, we'll see that it may not be linear. And there are multiple reasons behind this, but one of them is that the best predictor may need to draw on the dependencies between the variables. And if those dependencies are not linear, then even if I have a linear data generating mechanism, I get a nonlinear predictor. So the point here being that quickly I'm going to get into complicated prediction settings. And then even if I make even more assumptions, and even if I say, well, assuming that my data are Gaussian, the generating process is linear, generative process for the fully observed data is linear, and then if we do the math, what we'll find is that even in this setting, the optimal predictor ends up being a polynomial of x, the observed data, and cross product of m, which is the mask of whether a feature has been observed or not. And this polynomial has 2 to the power d terms if I have only d features. So the point here being that the interactions between the multiple features, whether they're missing or not, even in a linear setting, create extremely complicated predictors. So even in a linear Gaussian setting, I get extremely complicated predictors. So this is going to tell me that non-linear models are often going to be necessary because the optimal predictor ends up being nonlinear, even in the simplest situation. So given that, I can try to fix the predictor by trying to recreate fully observed data. So not trying to feed in unobserved data in my predictor. And for this, I need an imputation procedure that will work out of sample, that will work imputing data that imputing test data without adjusting its procedure, its parameters. So one of the problems of the classic imputation procedures is that they need the full data set, and you can't apply them. You can't learn the imputation on half of the data and apply it to the other half. And so there are a bunch of imputation procedures that are available in scikit-learn that can separate the train and the test. The simplest one is the mean imputation. And it's really a special case of univariate imputation. And the idea is really to replace the missing value by the mean of the feature, where the mean of the feature is computed on the training set. And so this can be done using a simple impute. And then we can do conditional imputation. Conditional imputation is the idea that you're going to model one feature as a function of other features. And this can be done actually using predictors. The idea simply is that you're going to iteratively predict one feature as a function of others. And in R, this is done in packages such as mice or misforest, and they're very classic packages. They're not very easy to use in a predictive setting because they're not very easy to separate learning the imputation from applying it. And in scikit-learn, this is done with the iterative imputer. And here, one of the challenges that we'll face is that it comes with a fairly bad computational scalability. And I'll come back to this. And there is also the KNN imputer in scikit-learn. So there are also other imputers. But scikit-learn comes with a bunch of imputers that can be learned on the train set and applied on the test set. Now, the classic statistical point of view is that you really don't want to use mean imputation because it distorts the distribution. So here I'm showing you a data set where I've done mean imputation, and you can see the imputed data. just lying on a line. And the reason is that the imputation has completely forgotten the variance. And from a theoretical point of view, it's because the imputation does not preserve the data properties that are needed by a later analysis. So in classical statistics, this is seen as really something that you don't want to do. Now, what we've shown recently is that actually, if you want to predict, this may not be a bad idea. And I'll come back to this later. But first, I want to discuss slightly more involved way of doing things, which is using a good conditional imputation. And so what we've shown is that if you have a good conditional imputation and you apply it to the test set, and actually you need to do this applying it, sampling also the variance to compute a full expectation. So basically resampling the train set and the test set. And if you do this, then you achieve the best possible predictor. Now, this may be hard to do in practice because you need a good conditional multiple imputation. And so I'll show you how to do simpler things. And to do this, we need to rethink our view of imputation. And because the point of view that I've shown you here is really a very classic point of view where I use imputation to compute expectations under the distribution of the missing values given the observed value. And this is hard. Okay, so one first very strong result is that if we use a very powerful learner, a learner that is known as universally consistent, so that can approximate any a data distribution, any regression function, then we can use a very simple imputation. So we can use, for instance, the mean of the train set to impute the missing values. And if we do this, the intuition behind this theorem is that if we do this and we use the powerful learner will just compensate for the shifts that we're including. Really, the intuition is that the learner recognizes the imputed entries and compensates them at test. Okay, so what I've just told you here is that if you're interested in prediction and you're using powerful learners, so not linear models, but things more complicated, you have very different trade-offs and you don't need to do a very good imputation. Now, if we go back to the results that we had before, it's important to keep in mind that if we use simple models, such as linear models, then constant imputation will not work. So you need complex models to be able to use simple imputation. And so we can test this with very, very simple examples. And we can compare really stupid imputation, which is a mean imputation, with a more complex imputation, which is the iterative imputer. And what we can see, so the iterative imputer is really trying to capture the dependencies between the different features. And so what we can see here is that the iterative imputer is useful for small sample sizes, but it's not useful for large sample sizes. Because for large sample sizes, here we're using a gradient boosted tree, and for large sample sizes, the gradient boosted tree simply captures well the imputed data, even if it's imputed as a mean. So this is not the end of the story, because in general, imputation is not enough. We can have the situation where the missing value is predictive of the output. So for instance, we can have a very pathological case where the output that we're trying to predict, Y, depends only on whether the data is missing or not. And for instance, this could be a tax fraud detection problem. Now, if we want to go back to the theory setting, this would be a missing not at random setting. But anyhow, here, if we impute the data, we're going to lose this information of that the data is missing. And so it's going to make our prediction absolutely impossible. So what I'm saying here is that in certain settings where the missingness is predictive of the output, imputing may be a terrible idea. And so the solution here is to add a missingness indicator. So basically we're going to impute, but on top of this, we're going to indicate that we have imputed by adding a specific column. And it's the same thing as the mask that I've mentioned before. And so this can be done in scikit-learn using the add indicator argument that's present in a bunch of the scikit-learn imputers. And here is a simulation where I'm looking exactly at this setting. And here we have missing data that depends indirectly on the missingness. So it's a slightly more subtle situation. And what you can see here is that if we do iterative imputer and we don't add the missingness indicator, it doesn't lead to good predictions because we've lost the information that the data was missing, and this information was useful for prediction. Now, if we add the indicator, it works well. And another interesting thing to note is that if we do mean imputation without adding the indicator, it also works extremely well. And the reason is that mean imputation actually doesn't lose too much information. Now, we can go one step further, and recently we shown a very broad result, which is that for almost any deterministic imputation function, for any missing values mechanism, so including in missing not at random setting, if you have a learner that's flexible enough, it will give you the best possible prediction. And really the idea is that imputation creates a specific structure in the data that can be captured by the learner. So we're really in a very different picture than the picture of classical statistics, because here we're not really trying to approximate the fully observed data distribution. We're trying to create structure that the learner can use to predict. And now, you could tell me, well, sure, but still, there might be better imputations than others. And one intuition, and it goes back to the classic intuition of imputation, is to impute the data where they're most likely. And it's not always clear that this is a good idea. And the idea here is that if my predictive function is not a linear function, it's a function with a curvature like a square, when I'm going to impute the missing value by its most likely value, I'm going to forget an error term. I'm going to forget some variance, which is it's back to the same picture that my imputation forgets variance. The fact that I'm going to impute many different things in a straight line. And if I do this, then this forgetted variance will be turned into bias by the square of my predictive function. And so really what we're seeing here is that our intuitions that we might have are not correct. It's not always good to really try to approximate the most likely value of the missing value given the observed. And rather what we see is that typically it's most useful to chain imputation with regression and adapt the two together. So we can look at this with very simple examples, and even with very simple examples, we can have an intuition of the problems. So here I'm showing you the fully observed data, and I've added as a color on it the value that I'm trying to predict. So this is the fully observed data, and we can see it's quite simple. It's a Gaussian, and the value that I'm trying to predict is a linear function of the two features. And so now this is the partially observed data, and we here I'm in missing completely at random settings, and in those missing completely at random settings, there's a structure in my partially observed data. So there's no bias between the fully observed data and the full data distribution. And now here I'm using my best possible imputer, which is the conditional imputation. And so the conditional imputation here is using a linear linear dependency between the imputed value and the observed value. And so what we're seeing is that it's creating straight lines, because it's imputing with the linear models. Okay, so we can see the straight lines are the lines of the imputed data. And so the first thing that we can note is those straight lines are clearly visible. The imputation is imperfect, and we haven't recovered the original data distribution. And so there is imputation imperfection, and this is going to make the regression hard. It's going to make the regression harder than the original problem. Now, if I go into a more difficult setting, and I go into missing not at random setting, where my values are unobserved in a way that is not independent from the underlying values. So you can see here that the values are unobserved, or most likely to be unobserved for large values of x1 and x2. We're dropping more data here. And if I do this, I build my imputation model, and my imputation model is actually even more imperfect. And it's not obvious why, but really what it did here is that it took some of the data points here, and it moved them to the left or down. And by doing this, it's breaking the relationship between those data points and the outcome. And so the way you can see it is that I have a line that's a lighter line on a dark background of points. So really I have a line where my outcome y is taking a value that is much larger than the surrounding y's. So it's creating a regression function that is very hard to learn. And so once again, what we're seeing here is that an imperfect imputation makes the regression really hard. And this setting is actually very frequent in real life, and we'll see this on real life experiments. And so really, this is the picture that you should have in mind. You know, we're using an imputation function, but this imputation function is imperfect. And because it's imperfect, it's going to make the prediction function that we're trying to learn even more complex and harder to learn. And that's a different setting than the one where we're trying to recover the fully observed data. Because what we're really trying to do here is that we're trying to find the simplest way of predicting the outcome. Okay, so I tried to discuss how we need to rethink the imputation. The point being that a good imputation is an imputation that makes the regression easy. It may be close to the conditional imputation, which is the one that is typically targeted by imputation software, but it might not be exactly this one. And with this picture, if we really, take the view that an imputation doesn't, find the clean or correct data, but rather makes the regression easier, then this picture can work even in missing not at random settings. Whereas classic imputations fail in missing at random, not at random settings. Now we could think, but actually maybe a good imputation will help interpretation, and maybe we should still be imputing to facilitate interpretation. And here the discussion is a bit difficult, because if we get a really good imputation, then yes, interpretation is really easy. I found the missing age of the person, and hence I can reason on my model as I had the actual age. Now the problem is that quite often in real life we have imperfect imputations, and those imperfections will propagate in the model, and so we'll be interpreting the imperfections. So I've discussed in length imputation, and now I'd like to discuss predictive modeling without imputation. And to do this, we need models that can readily account for missing values. And so that's not the case for every model. It's only for specific models, which I'll cover here. And I'll really focus on the models that are based on trees. And so trees can be quite easily adapted to work with missing values. So really, any tree-based model, the way it works is that it builds a set of simple decisions, basically binary decisions, typically looking at the value of each feature and making decisions on whether the value of each feature is larger or smaller than a specific threshold. This threshold is learned at train time. And so what's possible is to change a bit the way those decisions are made by learning to make these decisions accounting for missingness. And so the way this is done is by first, learning the optimal decision for the fully observed data, and then afterwards deciding whether, when the data is missing, it should be considered as going to the right of the tree or the left of the tree, or even a specific branch. So we're really, creating a tree that is specialized to account for missingness, and this tree is optimized on the training set. One reason why this tree can be optimized on the training set is that the underlying approach is really a greedy approach that doesn't really need any specific structure in the data. So this is known as the missing incorporated attributes, and it's implemented in XGBoost or in the his gradient boosting classifier or regressor of scikit-learn. And in practice, this is a really good option. It works really well. It's really just learns to model the missing values inside the trees, and can be used readily without any imputation, without any difficulty. So we can benchmark this. And so here we're benchmarking on a very simple situation. We're benchmarking this on a missing completely at random situation. And we're comparing to the things we've seen before, which is mean imputation or iterative imputation. And we're looking at this as a function of data size. And so what we can see here is that if we have plenty of data, everything works well. But if we don't have much data, even in this very simple missing completely at random situation, the imputation inside the tree actually works extremely well. It works much better than the other options. And so this is, of course, a very simple benchmark, but it matches kind of my experience on many data sets, and we'll come back to it. Now, if we benchmark a harder situation, which is one where we have missing not at random values and specifically censoring, then the benchmark is richer. And here we may need to add, as we did before, the indicator of the missings. And if we do this, we can see that adding the indicator, as we've seen before, it kind of fixes the prediction. And if we have enough data, prediction works well on imputed data because we've added the indicator. But really modeling the missing value inside the tree is really what works best, even with a small amount of data. So it works best in missing at random settings and in missing not at random settings. And once again, missing not at random settings tend to break imputation methods unless we modify them to expose this information to the subsequent learner. Okay, so all this was based really on toy examples, and now I'd like to discuss a bit results on real data. And so this was work that was done by a PhD student in my lab, Alexandre Perez-Lebel, and it was published in GigaScience, so it's openly available. The publication is openly available. It's a very rich publication. I'll just cover a few main results. And now the important point was that we used real life data. We focused on health databases, and we used a bunch of them. We used 4 different health databases and 13 different prediction tasks. So the goal here is to have results that are more general than a single data set. And so we did the validation well, in the sense that we did a nested cross validation, making sure that we always impute on the test set, using a model that has never seen the test set. So we're really careful to avoid data leakage between the training and the test set. Now, a first result that I won't cover here, but that's in the paper, is that the gradient boosted trees worked much better than the linear models. This may be because we had many categorical columns. This was a real data set with all its complexity. But really, on these data sets, linear models were not very competitive to gradient boosted trees. Okay, now this is the kind of results that I'll be showing. Each of the colored line here corresponds to a given data set. And so what we're seeing here is trends across multiple data sets. And we've benchmarked a bunch of different methods. On top is the missing incorporated attribute, so the handling the missing values inside the trees. And then we have a bunch of different constant imputation methods with and without the mask or the indicator. And here we have a bunch of different conditional imputation methods, including the KNN imputer, which I hadn't benchmarked so far. And so bigger is better. So what we're seeing here is that, well, missing incorporated attribute tends to work slightly better than the others. And in general, we can see that adding the mask is important in many settings. So the fact that adding the mask is important in many settings is telling us that, those settings are probably not missing at random. They're probably missing not at random. And I think this is a fairly general case of real data. Real data is seldom missing at random. The reason statisticians like so much the missing at random assumption is that it's needed for a lot of the maximum likelihood methods and related approaches, such as imputation, to work. So it's really driven by the needs of the statisticians rather than the data. So we've done this with different data sizes. So as the different graphs that I'm showing you here are graphs where we're increasing the data size, and as we increase the data size, we're kind of seeing that the gaps evolve. The lead of MIA is kind of decreasing, and it's a bit closer to constant imputation with masks. And so if we do this, including to very large data sizes, what we can see is that really the two methods that tend to stick out and work well are the missing unincorporated attribute and the iterative imputer with the mask. Okay, so those are the two really that stick out, but constant imputation with mask work well also. Here, I'm going to come back to this, but we could not run the GAEL imputer, and I'll come back to it. Okay, so if we look at computational performance now, and computational performance is something important because running those training and testing those models may be costly. What we're seeing really is that the constant imputations without the mask and the MIA are really the less costly in terms of computational time, and the iterative imputer and the KNN are the most costly. And if we increase the data set size, those differences just amplify, and to a point where the cost of the iterative imputer and the cost of the KNN imputer become very, very high. Specifically, the KNN imputer increases very fast because it's got a computational dependency that goes as n squared, where n is the size of the data set. So here it was just impossible. It was intractable to run the KNN imputer. So those things are extremely costly, and on top of this, they don't predict very well. So they're not very useful. And same thing for the iterative imputer, where the cost grows, so it doesn't grow as fast as the KNN imputer, but it grows quite nastily, and it becomes absolutely intractable for large databases, especially databases that are large in both directions, in both the number of features and the number of samples. And so here the problem is that when we try to use sophisticated imputation methods to really do the best possible imputation, it becomes extremely costly. And on top of this, it doesn't really improve prediction because, as I mentioned before, the important thing is to enable the learner to capture the missing values and to use them for prediction, which the missing incorporated attribute does very well. So my personal view is that if I can, I will really focus on using missing incorporated attributes rather than use sophisticated imputation methods that are going to be very expensive and may not predict very well. And this is evidence on real life data. And once again here, I'm showing the results for the prediction performance, and for the prediction performance, the missing incorporated attribute is working very well. So both for computational performance and for prediction performance, it's a good trade-off. Another thing that we can see is that in real life data, we really need to add the missingness indicator because the values are because the missingness is not missing at random. Now, one question that we may ask is, what about multiple imputation? Multiple imputation is, for statistical estimation, considered as the go-to standard. can we improve those results with multiple imputation? And so the way we've done this is to build a predictor with multiple imputation. We've estimated many models. So to estimate many models, once you've estimated many models, then you need to apply them on the test data to predict. And this leads to what's classically known in machine learning as model aggregation. And how to learn those many models? Well, the way we did it was that we used bootstrapping. So we bootstrapped the data. And so this led to multiple imputation models and then multiple prediction models. And then we aggregated the results. So this is really what's known as bootstrap aggregation when we're doing this. And bootstrap aggregation is bagging, a well-known machine learning trick. And if we do this, it works well, but typically if we do 100 bagging, then we have multiplied by 100 our compute costs. So the compute cost can go very, very high. So does it work in practice? Well, in practice, it does work. It improves significantly, markedly the prediction accuracy. And the fun thing is that it does this for every possible approach. So basically, for every possible approach, bagging improved significantly the prediction accuracy. So we're not really sure this is a result on multiple imputation or a result on bagging. And the reason why we're not sure it's a result on multiple imputation is because this worked even for MIA, missing incorporated attribute, where there's no imputation. So we're not really sure that the classic intuitions of multiple imputation carry over here. And so the result stays true, including for very large data sets. So the fact that bagging plus MIA works better than iterative imputer plus bagging, which we can see here, is somewhat telling us that approximating the conditional distribution is not really the important thing to do here. Okay. If you have any questions, please ask them in the chat. I'm monitoring the chat. And if there are no questions, then I'll just move forward to slightly more bleeding edge results. So neural networks, I know that neural networks are popular, and we've studied them, and we've studied how to build prediction. So build neural networks prediction with missing values. So first, let me set a bit the intuitions. The challenge, so the goal here is with neural networks is to do models, continuous models. Neural networks are continuous models that are optimized with gradient descent. This is one view of neural networks. And the difficulty is that when we have missing values, we have a half discrete input space. And we'll see that this leads to specific challenges with a very simple example. So here I'm showing the simplest possible setting where the output y is a linear model of the two inputs, and the two inputs are correlated. And if one of the inputs is missing, then the best predictor should compensate for this missingness by putting more weight on the other output, on the other input. And so when we do this, we can see that the weight of the model must adapt to the number of inputs that are missing. And so once again, as I've mentioned before, this gives us up to 2 to the power d set of weights, because that's the number of possible combinations of missing values. Okay, so really each time we have one value that goes missing, we need a specific set of weights to compensate for this missing. And really this is the difficult thing, because it means we have a very complex function to learn. And so what we did is that we looked at neural networks, neural network architectures that would approximate the optimal predictor. So a predictor that has the property that I just mentioned before. And to do this, and I'll skip the details, but we did the math to compute the optimal predictor in simple settings. And the goal here is to learn a tailored architecture which learns all the slopes together. And so this tailored architecture, we called it NUMIS because it's based on Newman series, but that's a detail. And so what we can show here is that NUMIS needs much less data and much less parameters to learn a good prediction setting than using, for instance, MLPs, multi-layer perception. And the reason really is that it learns all the slopes jointly. Another important result is that it works both for MAR and NAR settings, so missing at random and missing not at random setting. So this is detailed in the paper, but the reason is that the parameters of the model are directly optimized on the data. And because they're directly optimized on the data, they can capture the specificities of the data, including the fact that there are specific shapes in missing. Okay, so here, one thing that we could do is that we could cover a fairly didactic set of notebooks that I have online. This is the best way to learn. But for this, I would really like to hear, what are the most interesting points to cover. If there are any questions, if everything was clear, if everything was not clear. So please, tell me in the chat what exactly you would like me to cover. We have another like 20 minutes to go. If I see no reaction, I think I'll just go on with the presentation and maybe potentially finish early. Okay, well I'll go on, and if people want me to cover those notebooks. Oh, yes, someone's typing. I know remote makes everything harder, but it's always good to have interactions with people. Elsewhere, we could just be doing YouTube videos. For survey datasets, so I have a question that asks me whether for survey datasets, it is okay to assume that the data is missing at random. Most likely not. Most likely people will not reply to questions and are more likely not to reply to questions in certain settings. For instance, if I ask you a question on your revenue, you're more likely not to reply if your revenue is unusual. So if you're super rich, you're more likely not to reply. You're more likely to say, no, I would like not to answer this question. On the opposite, if your revenue is super small, you're more likely to also not want to answer. And that's going to be true of everything, of age, of everything. So it's typically, yeah, survey data sets, I would worry about the data being not missing at random. This is, by the way, I believe true of most data sets. Most data sets are not missing at random. The question is how close they are to missing at random. But if the data is missing, there's a reason for which it's missing. And you want to understand this reason, because this reason will tell you if you can assume things such as missing at random. Now, the good news is that if you take the machine learning perspective, where you're not trying to impute to recover the true data, but rather to help the prediction, you don't need the missing at random assumption. So thank you, by the way, for asking the question. It's more lively. So the notebooks. So the following question is whether it's okay to still apply imputation for missing values using the KNN imputation. Well, first, I would not go for the KNN imputation. If your data is not tiny, it will be intractable. In theory, it's not clear that imputing will give you valid results. You need missing at random settings to have valid results with imputation. Now, in practice, if your predictor is a rich one, it can learn to predict well, despite the fact that the imputation is imperfect. But you should assume that your imputation will be imperfect, and you should assume that your predictor needs to compensate for this. I'm personally, for prediction, I'm personally really in favor of using very simple imputation methods, and maybe no imputation method, and a model on top of this that's a rich one, such as tree-based models. Now, of course, this is a different trade-off than the one that is typically taught, but the one that is typically taught is really anchored in classic view of statistics. Any other questions, anyone, please? Feel free, I'm reading the chat and I'm very happy to get questions. And in the meantime, while I'm leaving time for possible questions, I'll point out that the notebooks that I'm using here are available online at dirtydata.science, and there's a set of Python notebooks, and one of them is on machine learning with missing values. So they're available online, and if you go to the bottom, you can also launch them in a binder. There we go. So a binder here, where a binder instance is a way of running the notebooks online. So while I wait for other questions, let me quickly say what this notebook is about. This notebook is really about having very simple examples that reveal the different mechanisms that we've discussed. And so really it's a very simple type problem where we generate the data ourselves, and it's the data that I've shown before, where we have two features and a value y that depends on those two features. And really in the notebook, what we do is that we generate different set of missingness mechanism, starting from the most simple one, which is the missing completely at random setting. And it's very simple simple data set. You know, it's a small size. We have n equals 500, and even small size, we can see some of the phenomena that I was discussing during this course. So we can, for instance, use an iterative imputer, and we can see that the iterative imputer isn't perfect. We could use a KNN imputer. Maybe we should. That would be interesting. I frown on KNN imputer because it will not be scalable for large data set sizes. And the important thing is that in this notebook, we're really focusing on looking at the predictive accuracy of a model on top of the imputed data. And that's something important, because our goal is not to get the best imputed data, but really to build the best predictive. And so here we can see what a simple imputer does. We can see how much it distorts the data distribution, but we can see that it actually leads to pretty good predictions. And the reason why it leads to pretty good prediction is that it's simple to capture those values into special case them. And finally, here we're using the missing incorporated attribute, and we can see that it leads to good prediction accuracy. And here we visualize different prediction accuracies. Actually, I was wrong, and in this setting, the gradient boosting regressor, which uses missing incorporated attributes, actually leads to worse prediction accuracy. And the reason is that our data set size isn't huge, and the gradient boosting regressor doesn't have enough data to learn well the prediction function. Okay, so this is a good counterexample that when we have a small data set, good imputation is probably the best thing we can do, because we can't learn the complex models. So here, small data sets is 500 samples. It's also a simulated data set, so it's simpler than the real data set. And here, if we go to larger data sets, so 20,000 samples, we can see that the picture changes. And with a larger data set, really the gradient boosting regressor actually is able to outperform the iterative imputer with a linear model. And what we can see, by the way, is that the constant imputer with a linear model is always underperforming, and the reason is the theoretical one that I mentioned, that you need a complex model to be able to learn from a simple imputation. Okay, and then the notebook covers missing not at random setting, and in the missing not at random setting, so here we create some form of censoring mechanism where it's more likely to have missing values for high values of x1 and x2. And this is what I mentioned before, the imputation distorts not only the data distribution, but also the link between x and y. And so now we can do small benchmarks, which you can very easily reproduce. And what you can see here is that in those settings, really the ridge imputer really doesn't, well, the ridge model with the different imputers really doesn't work well. And the reason is because what we have now modeling errors. We have now a model because of the systematic missingness that is no longer a simple model, and hence the reach just doesn't work. And I think this is very common in practice. And this was done with it was done with 20,000 data points, so it's a fairly large data set. Okay, so really this you can play with this notebook as an exercise. It's a very simple way of understanding all the things that I've discussed in my course. And I'll go back to my slides, and I will wrap up. But there's one more thing that I want to cover. Is really this notion of bias, and this bias may come from anywhere. It's the fact that you're not measuring all the units that you would like to measure. For instance, you can have this when you have missing outputs. Missing outputs, I can't use them in training. If I have missing Y, I can't use it in training. And so if I do this, the only thing I can do with the tools that I have is to drop those lines, to drop those units. But if I drop those units and those units are not missing at random, then I'm creating some form of bias. I'm creating some form of censoring because we get a data set loss that is related to the process understood. And there's a very famous example that was studied during the Second World War. People were looking at the planes that came back from the battle, and they were looking at where the bullets were. And the naive conclusion would be to say, well, this distribution of bullets is representative of where the bullets hit on the plane. But that's not true, because we're missing the most important planes. The planes where there was a bullet that hit, say, the engine. We can see here that there's no bullet on the engine. There's a bullet that hit the engine, and that plane never came back. So we've lost data points, and our conclusion does not account for those lost data points. So the classic problem of bias in general, and in specific settings of censoring, which can be studied by a specific set of models, which I haven't covered because it would be too much for this presentation, which are survival models. So they're known as survival models, and there's a Python package for this, which is known as the Lifeline package. And so once you start having the drop of data in the outcome, you need to wonder whether this drop of data in the outcome is at random, and if it's not at random, you need to use specific models. Okay, so to recap, I've really covered prediction with missing values, or learning with missing values. I would like to stress that imputation is theoretically motivated only in the MAR setting. Outside of the MAR setting, the theoretical motivation of imputation is no longer a solid one. One thing that we've learned over the time studying this is that rather than a sophisticated imputation, it's better to use a powerful supervised learner. In many practical cases, not all, but many, as long as you have enough data, the scikit-learn's his gradient boosting classifier or regressor can readily model missing value and is the best practical option. And one good thing is that it can work even in missing not at random settings. So really, I like to stress that we're in a different regime than standard statistics. And as I mentioned, there was notebooks online that you can use to have intuition. So we have a bit of time, so I've put references here, but maybe the most important, if you're not interested in theory, is the one by Alex Perez de Belle on the benchmark. because this benchmarking paper is full of practical tricks. Are there any questions? We still have a bit of time, so if there are any questions, please ask them. Questions or comments, anything that you'd like me to cover, please ask them on the chat. This was clear. I know this is a lot of information. It was maybe a bit theoretical, but this theory is useful to understand what you're doing. I see that someone is typing. But there's a question on time series data. I haven't looked at time series data. I suspect you're going to have the same kind of trade-offs, which is that if you have this, some form of systematic missingness that happens, it's going to make everything much harder. I also suspect that you have a lot of structure on time series data. Typically, you have some form of temporal structure, and that temporal structure should be used by the imputation. So people do things as simple as keeping the last value. Keeping the last value may not be very robust. There are very complicated imputation packages that work with missing values. I wonder whether I would not advise in any cases to, even if you impute, always expose the missingness indicator. I think this is really an important a message that comes out of both the theory and the practice. And then I guess I don't have enough experience with the kind of mechanisms that may happen in time series data. In here, really, the question would be, try to understand the mechanism, try to understand if you're in a setting where you're more likely to be somewhat missingness with no bias, so missing at random, and also try to use rich predictive models after your imputed data. If anybody has any question, now is the time, because we are going to run out of time after a while. I don't know if my answer was clear to the time series. So anybody who's giving me feedback, thank you very much. It's sometimes a bit hard to speak to a computer. We're in the process of adding a very, very simple version of those recommendations in the scikit-learn in the scikit-learn documentation. However, some of the messages are absolutely general and totally go beyond scikit-learn. And XGBoost, for instance, implements also the missing incorporated attribute. XGBoost is available in R. This is the ideas are general ones. Imputation of missing data in general is only valid for missing at random settings. It doesn't need to be missing completely at random. You can, in theory, build imputations that are valid for missing not at random, but then you need to model the missingness mechanism. So if you have a specific model of the missingness mechanism, if you're able to say, well, if you're able to capture the fact that a value may be more likely to be missing if the corresponding feature has a high value, then you can build specific imputers that correct for this. But most of the imputers that are available off the shelf, by a vast majority, don't do this. There's a difference between the theoretical answer that tells you, well, you can actually build imputation that is valid for missing not at random, and the practical answer that tells you, well, yes, but most of the tools will not be valid. So I would in general worry of imputing if your data is severely missing at random, if you have some form of severe censoring bias. And I would always try to add an indicator just to see if it improves prediction or not. So between us, supervised learning with missing values isn't terribly difficult. You just use a his gradient boosting regressor and you're done. I'm kind of simplifying things, but you know, in practice, it's often a good option. And I've given you the reasons why. So in a few minutes, I'll have to run because I have another meeting that is related to my day work, my real work. For attending. I hope this was helpful.